Right now, 26,000 light years away, something is pulling at you. Every atom in your body, every breath you take, every step you walk is being influenced by an invisible monster lurking at the heart of our galaxy. We thought we lived in a peaceful cosmic neighborhood. We were catastrophically wrong. For centuries, when humans looked up at that hazy band of light stretching across the night sky, they saw beauty and mystery. Ancient civilizations called it the River of Souls, the Path of Spirits, the backbone of the night. They had no idea they were staring directly at the most violent, most destructive, most absolutely terrifying object in our local universe. Something so massive that it defies every intuition about reality. Something so hungry that it devours entire star systems for breakfast. Here's what makes this deeply disturbing. The object I'm talking about contains the mass of 4 million suns, compressed into a space smaller than our solar system. Its gravitational pull is so intense that if you could somehow survive getting close enough, time itself would slow to a crawl. Light, the fastest thing in the universe, cannot escape its grip. And this cosmic predator sits at the exact center of everything we call home. But here's the revelation that will change how you see our place in the cosmos forever. This monster isn't our enemy. It's our creator. Without its gravitational architecture, the Milky Way wouldn't exist. Without its invisible influence, stars wouldn't form in the patterns they do. Without its presence, you wouldn't be here watching this video. The most dangerous object in our galaxy is also the reason you exist. Tonight, we're about to embark on a journey to the most forbidden region of space. We'll discover how scientists finally pierced through 26,000 light years of cosmic dust to glimpse the unseeable. We'll witness stars being torn apart in real time. We'll explore what happens when matter crosses the point of no return. And we'll uncover why this invisible monster might hold the key to understanding not just our galaxy, but the nature of reality itself. The evidence I am about to share with you comes from decades of detective work by the world's most brilliant minds. Teams of astronomers have spent entire careers tracking individual stars as they dance around something they cannot see. They've built telescopes powerful enough to spot objects smaller than our solar system at distances that would make your head spin. They've detected gravitational waves rippling through spacetime itself, all to answer one simple question that turns out to have the most complex answer imaginable. What they discovered challenges everything we thought we knew about physics, about time, about the structure of reality. The center of our galaxy isn't just a place. It is a laboratory where the laws of the universe are pushed to their absolute limits, where Einstein's theories either triumph or shatter completely, where space and time become so warped that cause and effect lose their meaning. Dr. Andrea Ghez, who won the Nobel Prize for this work, described it perfectly. We're looking at physics in the most extreme environment possible. When you peer into the galactic center, you're not just looking at astronomy. You're looking at the fundamental nature of existence itself. As we journey deeper into this cosmic mystery, you'll discover that the question, what is at the center of the Milky Way, doesn't have a simple answer. The center of our galaxy is simultaneously empty space and the most massive object imaginable. It's both completely invisible and the brightest radio source in our sky. It's a region where everything we understand about reality breaks down, yet somehow continues to work perfectly according to laws we're only beginning to comprehend. If you're refascinated by the most extreme objects in the universe and want to understand how they shape everything around us, subscribe and hit the thumbs up button. And here is something to think about. If you could somehow survive a journey to the galactic center, what do you think would be the last thing you'd see before crossing the event horizon? Comment below. I'll pin the most mind-bending answer. The journey we're about to take will challenge your imagination at every turn. We'll start with the mystery that puzzled astronomers for generations. Then follow the scientific detective story that led to one of the most important discoveries in human history. By the end, you'll understand not just what lurks at the center of the Milky Way, but why its existence changes everything we thought we knew about our cosmic home. Now let's begin our descent into the heart of the galaxy, where the impossible becomes inevitable, and where the most fundamental question of our existence finds its most profound answer. Chapter 1. Hidden Center. When you look up at the Milky Way on a clear night, you're seeing only the faintest glimpse of something magnificent and terrifying. That ghostly river of light stretching across the sky represents the edge-on view of our spiral galaxy, home to over 400 billion stars. But here's what your eyes cannot see, what humanity remained blind to for thousands of years. The most important part of this cosmic structure is completely invisible from Earth. The center of our galaxy lies hidden behind an impenetrable wall of dust and gas. Imagine trying to see through a thick fog that stretches for thousands of light years in every direction. This cosmic fog doesn't just block visible light, it devours it completely. The dust particles floating in interstellar space absorb and scatter photons so effectively that looking toward the galactic center in optical light is like trying to see through a brick wall. This cosmic concealment created one of astronomy's greatest challenges. For centuries, scientists could map the spiral arms of distant galaxies with ease, but remained completely ignorant about the structure of their own galactic home. They could see the edges, the spiral arms, the outer regions where stars shine clearly through relatively empty space. But the heart of the Milky Way remained as mysterious as the far side of the moon. The breakthrough came when astronomers realized they needed to see with different eyes. In the 1930s, Carl Jansky made an accidental discovery that changed everything. While trying to identify sources of radio static that were interfering with transatlantic telephone calls, he detected mysterious radio waves coming from the direction of the galactic center. Unlike visible light, radio waves pass through cosmic dust as if it doesn't exist. This revelation sparked a revolution in astronomy. Scientists began building radio telescopes, massive dishes designed to capture these invisible signals from space. What they discovered was extraordinary. The galactic center wasn't quiet and empty as it appeared in visible light. Instead, it was screaming with radio energy, more active and violent than anywhere else in our galaxy. By the 1960s, radio astronomers had mapped a complex landscape of gas clouds, stellar remnants, and mysterious compact objects clustered around something they couldn't yet identify. The radio signals revealed a region of space unlike anything else in our galactic neighborhood. Something was energizing vast clouds of gas, accelerating particles to nearly the speed of light, and creating magnetic fields thousands of times stronger than anything found on Earth. But radio waves, revolutionary as they were, could only reveal so much. The true breakthrough required an even more exotic form of light: infrared radiation. In the 1990s, new infrared telescopes began piercing deeper through the cosmic dust than ever before. These instruments could detect the heat signatures of individual stars, even those buried deep within the galactic center's dusty veil. What astronomers saw through these infrared eyes was breathtaking. The galactic center wasn't empty space punctuated by mysterious radio sources. It was a dense stellar metropolis, packed with stars in concentrations that defied imagination. Near the very center, stars were crowded together so tightly that their average separation was only a few light hours closer than the planets in our solar system. These weren't ordinary stars either. Many were massive giants, some containing dozens of times more mass than our sun, others with the exotic remnants of stellar death. Neutron stars with magnetic fields trillions of times stronger than Earth's, and white dwarfs so dense that a teaspoon of their material would weigh as much as a car. The galactic center was revealed to be a cosmic zoo of the most extreme objects in the universe. But the most important discovery was still hidden. Among all these exotic objects, astronomers began noticing something even more extraordinary. A small group of stars near the absolute center of the galaxy were moving in a way that made no sense. These stars were orbiting something invisible, something compact, something so massive that it defied every theory about stellar evolution. The stars weren't just orbiting slowly over millions of years, as you might expect for objects separated by vast cosmic distances. Some were completing entire orbits in just a few decades. Their velocities reached thousands of kilometers per second speeds, so extreme that if Earth were moving that fast, we could travel from New York to Los Angeles in less than 2 seconds. To put this in perspective, imagine watching a bird fly around an invisible object in your backyard. Except this bird is the size of our entire solar system, and it is moving so fast that it completes a full circle around this invisible something every 20 years. The only way this could happen is if the invisible object contained more mass than you could possibly imagine, compressed into a space smaller than you could possibly conceive. Dr. Reinhard Genzel, who shared the Nobel Prize for studying these stellar motions, described the moment of realization. We were watching stars dance around something that shouldn't exist according to classical physics. The observations revealed that whatever lurked at the galactic center contained the mass of 4 million suns, packed into a region no larger than our solar system. As astronomers tracked these stellar orbits year after year, the evidence became undeniable. The stars weren't orbiting a cluster of objects or a dense collection of ordinary matter. They were orbiting a single point in space, something with the gravitational influence of millions of suns, but the size of almost nothing. The only theoretical object that could satisfy these extreme requirements was something that had been predicted by Einstein-bending equations, but never directly observed: a supermassive black hole. The realization was both thrilling and terrifying. At the heart of our peaceful galaxy, the cosmic structure we call home, lurked the most destructive force in the known universe. A gravitational monster so intense that it warps space and time into impossible geometries. An object where the familiar laws of physics break down and reality itself becomes negotiable. Yet this discovery was only the beginning. Identifying what sat at the galactic center was just the first step in understanding one of the most profound mysteries in modern science. The real questions were only starting to emerge. How did such a monster form? How does it influence the entire galaxy? And what does its existence mean for our understanding of the cosmos? As we'll discover, this invisible predator at the heart of our galaxy is far more than just a cosmic curiosity. It's the gravitational engine that shapes everything around us, the dark architect that has been designing our cosmic neighborhood for billions of years. But first, we need to understand how humanity even began to suspect that such impossible objects could exist. Chapter 2: Ancient Mystery. Long before telescopes revealed the truth about our galactic center, brilliant minds were already predicting the existence of objects so strange they seemed like science fiction. The theoretical foundation for understanding what lurks at the heart of the Milky Way was laid not by astronomers peering through telescopes, but by mathematicians working with nothing more than pencil and paper. In 1783, an English clergyman named John Michell made a calculation that would prove prophetic. Using Newton's laws of gravity and the known speed of light, Michell wondered, what would happen if an object became so massive and compact that even light couldn't escape its gravitational pull? He calculated that if you compressed enough mass into a small enough space, you could create what he called a dark star, an object completely invisible because no light could ever leave its surface. Mitchell's dark stars were mathematical curiosities, theoretical objects that existed only in equations. Few scientists took them seriously. After all, how could something be so dense that it trapped light itself? The idea seemed to violate common sense. Light had no mass, so how could gravity affect it? For over a century, Mitchell's dark stars remained forgotten footnotes in scientific literature. Everything changed in 1915 when Albert Einstein published his theory of general relativity. Einstein revealed that gravity wasn't really a force at all, but rather the curvature of space and time itself. Massive objects do and pull on other objects. They warp the fabric of space-time so dramatically that straight lines become curves. Light, traveling in what it perceives as straight lines, actually follows these curves through warped space-time. Einstein's equations were so complex that even he struggled to find solutions to them. But just months after publication, a German physicist named Karl Schwarzschild found an exact mathematical solution that described space-time around a spherically symmetric mass. Schwarzschild's solution was elegant and precise, but it contained something deeply disturbing. The equations predicted that if you compressed any mass into a small enough radius, something catastrophic would happen to space-time itself. At a certain critical distance from the center now, called the Schwarzschild radius, the curvature of space would become so extreme that nothing, not even light, could escape. Space and time would become so warped that the normal concepts of cause and effect would break down completely. Schwarzschild himself died on the Russian front during World War I, just weeks after making his discovery. He never lived to see the profound implications of his mathematical solution. For decades, physicists assumed that the disturbing predictions of Schwarzschild's equations were mathematical artifacts, impossible extremes that could never occur in the real universe. The resistance to accepting these objects was understandable. The Schwarzschild solution predicted the existence of what we now call black holes, regions of space where matter becomes so concentrated that it creates an inescapable gravitational trap. At the center of such an object, the equations predicted a point of infinite density and infinite curvature, a mathematical singularity where the laws of physics simply stopped making sense. Throughout the 1920s and 1930s, most physicists believed that nature would somehow prevent such extreme objects from forming. Surely, they reasoned, there must be some mechanism that would stop matter from collapsing beyond a certain point. The idea of infinite density seemed like mathematical madness rather than physical reality. The first crack in this skepticism came from studying stellar evolution. By the 1930s, astronomers understood that stars were giant fusion reactors, burning hydrogen in their cores to produce the energy that makes them shine. But what happened when the fuel ran out? When a massive star exhausted its nuclear fuel, what could stop gravity from compressing the star's core to unimaginable densities? Subramanian Chandrasekhar, a brilliant young astrophysicist, calculated the maximum mass that a dead star could support through quantum mechanical pressure. Above this limit, now called the Chandrasekhar limit, no known force could prevent gravitational collapse. For stars massive enough, the core would collapse completely, possibly creating the very objects that Schwarzschild's equations had predicted. When Chandrasekhar presented his findings to the Royal Astronomical Society in 1935, he was publicly ridiculed by Arthur Eddington, one of the most respected astronomers of the time. Eddington declared that there should be a law of nature to prevent a star from behaving in this absurd way. The scientific establishment wasn't ready to accept that the universe could create objects so extreme they defied physical intuition. But the mathematics didn't care about human comfort. Throughout the 1950s and 1960s, theoretical physicists like John Wheeler, Roger Penrose, and Stephen Hawking developed increasingly sophisticated models of gravitational collapse. Their calculations confirmed the disturbing implications of Einstein's equations. Under the right conditions, matter would indeed collapse into objects of infinite density and zero volume. Wheeler, who coined the term black hole in 1967, described these objects in language that captured their otherworldly nature. A black hole, he wrote, is a region of space where gravity has become so strong that nothing, not even light, can escape. It's a place where space and time lose their familiar meaning, where the very concept of inside and outside breaks down. The theoretical predictions were clear, but finding these objects in the real universe remained an enormous challenge. How do you observe something that absorbs all light and reveals nothing about its internal structure? How do you detect an object whose defining characteristic is its complete invisibility? The answer came from understanding that black holes, while invisible themselves, would have dramatic effects on their surroundings. Matter falling into a black hole would heat up to millions of degrees, glowing brilliantly in X-rays before disappearing forever. Nearby stars would be pulled into eccentric orbits, accelerated to tremendous velocities by the black hole's gravity. Gas and dust would form swirling accretion disks, creating some of the most energetic phenomena in the universe. By the 1970s, astronomers had detected the first candidate black holes in our galaxy's stellar mass, objects created by the collapse of individual massive stars. These discoveries proved that black holes weren't just mathematical abstractions, but real objects that existed in our cosmic neighborhood. If stellar mass black holes could form from individual stars, what about the centers of galaxies, where millions or billions of stars were crowded together? The theoretical groundwork for understanding supermassive black holes was falling into place. Computer simulations showed that if you packed enough stars into a small enough region, their gravitational interactions would inevitably lead to the formation of increasingly massive central objects. Some stars would be ejected from the system, while others would spiral inward and merge with the growing central mass. Dr. Martin Rees, one of the leading theorists in black hole physics, explained the inevitability of this process. Wherever you have a large concentration of matter in a small volume, gravity will try to make it even more concentrated. There's a runaway effect that naturally leads to the formation of supermassive black holes. But theory was one thing. Observation was another. The galactic center remained hidden behind its veil of dust, and the technology to peer through that veil was only beginning to emerge. Scientists had the theoretical framework to understand what might lurk at the heart of our galaxy, but they needed revolutionary new instruments to test their predictions against reality. The stage was set for one of the most ambitious observational campaigns in the history of astronomy. Armed with Einstein's equations and powerful new telescopes, astronomers were about to embark on a decades-long quest to unmask the invisible monster at the center of our cosmic home. What they would discover would exceed even their most extreme theoretical predictions. Chapter 3. Forbidden Zone 26,000 light-years from Earth. There exists a region of space so hostile that it makes the surface of the Sun look like a comfortable vacation destination. This is the galactic center's immediate neighborhood, a cosmic war zone where radiation levels would kill you in microseconds, where magnetic fields millions of times stronger than Earth's twist space into impossible geometries, and where the very fabric of reality becomes so distorted that time itself moves differently than anywhere else in our galaxy. To understand just how extreme this environment is, imagine trying to observe it from Earth. The light from the galactic center that reaches your eyes tonight began its journey toward our planet when the first humans were developing agriculture. For 26,000 years, that light has been traveling through space at 186,000 miles per second, crossing a distance so vast that if you could drive there at highway speed, the trip would take over 300 billion years. But most of the light from the galactic center never reaches us at all. Between Earth and the galaxy's heart lies what astronomers call the zone of avoidance, a region so thick with interstellar dust that it blocks 99.9% of all visible light. This cosmic fog is made of tiny particles, each grain smaller than the wavelength of light itself. These microscopic obstacles scatter and absorb photons so efficiently that looking toward the galactic center in visible light reveals almost nothing. The dust itself tells a story of cosmic violence. These particles are the cremated remains of dead stars, the ash and debris scattered by stellar explosions that have been occurring for billions of years. Every grain of dust was once part of a star's interior, forged in nuclear furnaces and expelled into space during the star's death throes. The zone of avoidance isn't just an obstacle to observation, it's a graveyard of stellar civilizations. Breaking through this barrier required astronomers to develop entirely new ways of seeing. Radio waves, with their much longer wavelengths, can slip between dust particles that block optical light. When radio telescopes first peered toward the galactic center in the 1960s, they revealed a landscape unlike anywhere else in the galaxy. The radio sky near Sagittarius showed a complex web of glowing gas clouds, each one energized by processes so violent they defied explanation. The most prominent radio source, designated Sagittarius A, appeared as a bright knot of emission near the galaxy's geometric center. But Sagittarius A itself was complex, containing multiple components that suggested different physical processes at work. There was Sagittarius A East, a supernova remnant created by a stellar explosion roughly 35,000 years ago. There was Sagittarius A West, a spiral-shaped nebula of hot gas swirling around some central object. And then there was Sagittarius A asterisk, pronounced a star, a compact radio source that appeared as just a tiny point of emission, but radiated more energy than anything else in the inner galaxy. Sagittarius A* was precisely located at the dynamic center of our galaxy, the point around which everything else appeared to orbit. Whatever was generating these radio signals was compact, incredibly energetic, and sitting at the exact gravitational heart of the Milky Way. As technology improved, astronomers developed infrared telescopes that could peer even deeper through the cosmic dust. Infrared light, with wavelengths longer than visible light but shorter than radio waves, revealed the stellar population near the galactic center in unprecedented detail. What they saw was a cosmic metropolis unlike anywhere else in our galaxy. The stellar density near Sagittarius A* is almost incomprehensible. In our solar neighborhood, the nearest star to the Sun is over 4 light-years away. Near the galactic center, stars are packed together with typical separations of just light days or even light hours. Some regions contain millions of stars, packed into volumes smaller than our solar system. If Earth orbited a star in this environment, the night sky would contain thousands of stars brighter than Venus. But the crowding itself wasn't the most remarkable feature of this stellar neighborhood. The stars near the galactic center were moving with velocities that seemed to mock the laws of physics. Ordinary stars in the galaxy's disk orbit at speeds of a few hundred kilometers per second. Near the galactic center, astronomers detected stars moving at thousands of kilometers per second speeds so extreme that these stars should have been flung out of the galaxy entirely. Dr. Andrea Ghez, whose team spent decades tracking these stellar motions, described the challenge. We were trying to measure the positions of stars with precision equivalent to detecting a quarter on the surface of the moon. And we had to do this through the Earth's atmosphere, which is constantly shifting and blurring our view. The breakthrough came with the development of adaptive optics, a technology that uses lasers and computer-controlled mirrors to correct for atmospheric turbulence in real time. With these systems, ground-based telescopes could achieve resolution rivaling space telescopes, finally revealing individual stellar motions near Sagittarius A* with the precision needed to understand what was happening. What they discovered was a cosmic dance of unparalleled violence and beauty. Near the galactic center, stars follow elliptical orbits around an invisible central object, just like planets orbiting the Sun. But these stellar orbits are far more extreme than anything in our solar system. Some stars approach within just 120 astronomical units of the central object, closer than Pluto orbits our Sun. At closest approach, these stars reach velocities exceeding 5,000 kilometers per second, or nearly 2% the speed of light. The star labeled S2 became a particular focus of study. This massive star, containing about 15 times the mass of our Sun, follows an extremely elliptical 16-year orbit around Sagittarius A asterisk. At its closest approach in 2018, S2 came within 120 astronomical units of the central object while moving at 5,000 kilometers per second. For comparison, if our Sun were moving that fast, it could travel from Earth to the Moon in just 15 minutes. But S2 wasn't alone. Astronomers discovered dozens of stars in similar extreme orbits, all circling the same invisible point with mathematical precision. These weren't random stellar motions caused by gravitational chaos. They were the orderly orbits of objects trapped in the gravitational field of something massive beyond comprehension, compact beyond imagination. The orbital mechanics revealed that whatever these stars were orbiting contained the mass of approximately 4.3 million suns, all concentrated within a radius smaller than our solar system. No collection of normal stars could achieve such extreme compactness. No cluster of stellar remnants could pack so much mass into so small a volume. The only theoretical object that could satisfy these observational constraints was a supermassive black hole. Yet even this identification was just the beginning of the mystery. The black hole at our galactic center wasn't behaving like a simple gravitational point mass. Radio observations revealed jets of material being ejected at near light speed. X-ray telescopes detected sudden flares of energy that brightened the central region by factors of hundreds within minutes. Infrared observations showed hot spots of gas orbiting just outside the point of no return at a significant fraction of light speed. The environment immediately surrounding our galactic center black hole was revealed to be one of the most extreme laboratories in the universe. Here, matter reaches temperatures of billions of degrees. Magnetic fields achieve strengths trillions of times greater than Earth's. Gravitational forces become so intense that space and time themselves are warped into geometries that would have seemed like pure fantasy just decades earlier. Dr. Reinhard Genzel, co-winner of the Nobel Prize for these discoveries, captured the profound nature of what was being observed. We were looking at the most extreme physics laboratory accessible to human observation. Near the galactic center, we can test Einstein-bending theory of relativity in gravitational fields stronger than anywhere else in the universe. The forbidden zone around our galactic center wasn't just a region of space to be mapped and cataloged. It was a cosmic laboratory where the fundamental laws of physics could be tested under conditions impossible to recreate on Earth. And at the heart of this laboratory sat an object so strange, so extreme, so utterly alien to human experience that understanding it would require revolutionizing our concepts of space, time, and reality itself. Chapter 4. Dark monster. At the exact center of our galaxy sits an object that challenges every human intuition about the nature of reality. It weighs as much as 4.3 million suns, yet occupies no space at all. It's the darkest object imaginable, yet it powers some of the brightest phenomena in the universe. It is simultaneously the most destructive force in our cosmic neighborhood and the gravitational architect that makes our galaxy's existence possible. This is Sagittarius A asterisk, the supermassive black hole at the heart of the Milky Way. To grasp the true nature of this cosmic monster, you need to understand what happens when matter becomes so compressed that the familiar laws of physics break down completely. A black hole isn't really an object in the conventional sense, and it's a region of spacetime where gravity has become so intense that it creates what physicists call a singularity, a point where density becomes infinite and the curvature of space becomes infinitely steep. The boundary around this singularity is called the event horizon, and it marks the point of no return. Anything that crosses this invisible barrier, whether it's a particle of light, a spacecraft, or an entire star, can never escape. The event horizon isn't a physical surface you could touch or see. It's simply the mathematical boundary where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing that crosses this boundary can ever return. For Sagittarius A*, this event horizon has a radius of approximately 12 million kilometers, roughly the size of Mercury's orbit around our Sun. Within this sphere of no return lies mass equivalent to 4.3 million of our stars, compressed into a mathematical point with zero volume. The density at the center is not just high, it's literally infinite, representing a breakdown of our understanding of physics itself. But here is what makes black holes truly alien to human experience. They don't just bend space, they fundamentally alter the nature of time. As you approach a black hole, time itself begins to slow down relative to the outside universe. This isn't science fiction, it is a direct consequence of Einstein's relativity that has been measured and confirmed in laboratory experiments. If you could somehow survive approaching Sagittarius A*, you would experience time dilation so extreme it defies imagination. From your perspective, falling toward the black hole, time would seem to pass normally. But to an observer watching from a safe distance, your clock would appear to slow down dramatically. As you approach the event horizon, they would see you moving slower and slower, your light becoming redder and dimmer, until you appeared frozen at the edge of forever. This time dilation effect has profound implications for understanding the galactic center environment. The region immediately surrounding Sagittarius A* exists in a state of temporal distortion, where different locations experience time at different rates. Matter spiraling into the black hole experiences time differently than matter farther away. This creates a complex dynamic environment where cause and effect become scrambled by the geometry of spacetime itself. The black hole's gravitational influence extends far beyond its event horizon. At a distance of about 3,000 times the event horizon radius, roughly the size of our solar system, the gravitational field of Sagittarius A* becomes strong enough to noticeably affect stellar orbits. This region, called the sphere of influence, contains hundreds of stars whose motions are dominated by the central black hole rather than by interactions with neighboring stars. Within this sphere of influence, the laws of celestial mechanics take on extreme characteristics. Stars follow highly elliptical orbits that bring them within a few hundred astronomical units of the black hole at closest approach. During these close encounters, the stars experience tidal forces so intense that they're stretched and compressed like cosmic taffy. Some stars are completely disrupted by these forces, their material torn away to form glowing streams that spiral into the black hole. The process of matter falling into a black hole, called accretion, creates some of the most energetic phenomena in the universe. As gas and dust spiral inward, they form what is called an accretion disk, a swirling vortex of superheated material that glows brilliantly across the electromagnetic spectrum. The temperature in these accretion disks can reach billions of degrees, hot enough to strip electrons from atomic nuclei and create a plasma more extreme than anything found in stellar cores. For Sagittarius A*, this accretion process occurs episodically rather than continuously. Most of the time, the black hole is relatively quiet, accreting material at a slow rate that produces only modest radio and infrared emission. But occasionally, something dramatic happens. A gas cloud wanders too close, or a star is partially disrupted by tidal forces, and suddenly, the black hole's feeding rate increases dramatically. These feeding events, called flares, can increase the luminosity of the galactic center by factors of hundreds within minutes. During a typical flare, Sagittarius A* consumes material equivalent to the mass of our moon, converting a significant fraction of that mass directly into energy according to Einstein's equation E equals mc. The energy output during these events exceeds the total power output of our Sun by factors of millions. Dr. Sarah Markov, a leading expert on black hole accretion, described the violence of these processes. When matter approaches a black hole, it doesn't fall in gently. It forms a hot, turbulent disk where magnetic fields become twisted into complex geometries. The result is a cosmic particle accelerator that creates some of the most extreme physical conditions in the universe. The magnetic fields near Sagittarius A* are particularly fascinating and terrifying. As electrically charged particles spiral around the black hole, they generate magnetic fields millions of times stronger than anything found on Earth. These fields become so intense that they can accelerate particles to nearly the speed of light and launch them in narrow jets that extend thousands of light years from the galactic center. Current observations suggest that Sagittarius A* may be launching such jets, though they're much weaker than those seen from more actively feeding supermassive black holes in other galaxies. These jets represent one of the ways that black holes can influence their surroundings, far beyond their immediate vicinity. High-energy particles accelerated near the black hole can travel throughout the galaxy, potentially affecting star formation and evolution across vast distances. Perhaps the most mind-bending aspect of black hole physics is how they challenge our understanding of information and causality. According to quantum mechanics, information cannot be destroyed. Every physical process must preserve the total amount of information in the universe. But black holes seem to violate this principle by permanently removing information from our observable universe. This contradiction, known as the black hole information paradox, represents one of the deepest unsolved problems in modern physics. Stephen Hawking spent decades working on this problem, eventually proposing that black holes might slowly evaporate through quantum effects, eventually returning all their information to the universe in a scrambled form. But for supermassive black holes like Sagittarius A*, this evaporation process would take longer than the current age of the universe, multiplied by trillions of trillions. The existence of Sagittarius A* also raises profound questions about the formation and evolution of galaxies. Computer simulations suggest that supermassive black holes and their host galaxies evolved together through a complex dance of gravitational feedback. The black hole's gravity helps organize the galaxy's structure, while the galaxy feeds material to the black hole, allowing it to grow over cosmic time. This symbiotic relationship means that understanding black holes is crucial for understanding galaxies, and understanding galaxies is crucial for understanding how structures form in the universe. The monster at the center of our galaxy isn't separate from the galaxy. It is an integral part of the gravitational architecture that makes the Milky Way possible. As we peer deeper into the nature of this cosmic predator, we begin to realize that calling it a monster might be misleading. Sagittarius A* is certainly dangerous and destructive on human scales, but from a cosmic perspective, it's more like a gravitational heart that keeps our galaxy alive and organized. Without its influence, the Milky Way would be a very different and possibly much less hospitable place. But the true test of our understanding would come from observing matter in its final moments before disappearing forever beyond the event horizon. What happens to space and time in the most extreme gravitational field accessible to human observation? The answer would require pushing observational technology to its absolute limits. Chapter 5. Gravitational prison. Imagine a prison so inescapable that not even light, the fastest thing in the universe, can break free once trapped inside. This isn't science fiction. It's the reality of what physicists call the event horizon, the invisible boundary surrounding every black hole that marks the point of no return. For Sagittarius A*, this gravitational prison extends roughly 12 million kilometers from the singularity at its center, creating a sphere of captivity more absolute than anything else in nature. The concept of an event horizon challenges every human intuition about boundaries and barriers. Unlike the walls of a physical prison, the event horizon isn't made of matter or energy. It's purely geometric, a mathematical surface defined by the curvature of spacetime itself. This boundary exists only because gravity has become so intense that it warps the fabric of reality into an inescapable trap. To understand how this trap works, you need to think about escape velocity, the minimum speed needed to break free from a gravitational field. On Earth, the escape velocity is about 11 kilometers per second. Launch a rocket at this speed or faster, and it will overcome Earth's gravity and escape into space. For the Sun, escape velocity is about 600 kilometers per second. For a white dwarf star, it might be several thousand kilometers per second. But for a black hole, the escape velocity at the event horizon equals the speed of light, 300,000 kilometers per second. Since Einstein's relativity forbids anything from traveling faster than light, nothing that crosses this boundary can ever escape. The event horizon is therefore an absolute prison, more final than death itself, because even information about what falls in can never return to the outside universe. What makes this gravitational prison even more disturbing is how it distorts the experience of time and space for anything approaching it. The closer you get to the event horizon, the more severely time dilates relative to the outside universe. This effect, called gravitational time dilation, means that time literally runs slower in stronger gravitational fields. If you could somehow survive falling towards Sagittarius A*, your experience would be profoundly different from what outside observers would see. From your perspective, you would fall through the event horizon in a finite amount of proper time, perhaps just a few minutes for a black hole of this size. You would see the stars behind you blue shift to higher energies, while the black hole itself would remain invisible ahead of you. But observers watching your descent from a safe distance would see something very different. They would watch your clock slow down as you approached the event horizon. Your light would become increasingly red-shifted, dimming and fading as gravitational effects stretch the wavelengths of photons trying to escape. To these distant observers, you would appear to freeze at the event horizon, your image growing fainter and redder until it faded below the threshold of detection. This strange difference in perspectives highlights one of the most counterintuitive aspects of black hole physics. The event horizon exists in a different temporal reality than the outside universe. In some sense, from the perspective of external observers, nothing ever quite reaches the event horizon. It appears to freeze at the boundary, taking an infinite amount of time to cross over. Yet from the perspective of the falling observer, the crossing happens in finite time. The tidal forces near the event horizon add another layer of horror to this gravitational prison. Tidal forces occur because gravity weakens with distance, so your feet experience stronger gravitational pull in your head if you re-falling feet first toward a black hole. For stellar mass black holes, these tidal forces would stretch and compress you like taffy long before you reach the event horizon, an effect colorfully termed spaghettification. Fortunately, for supermassive black holes like Sagittarius A*, the tidal forces at the event horizon are actually relatively gentle. Because the black hole is so large, the gravitational gradient across a human-sized object isn't as severe as it would be for smaller black holes. You could theoretically cross the event horizon of Sagittarius A* without being immediately torn apart by tidal forces. The spaghettification would come later as you approach the central singularity. But while the event horizon itself might not immediately destroy a human visitor, the environment surrounding it certainly would. The region just outside the event horizon is filled with high-energy radiation from the accretion disk, magnetic fields strong enough to disrupt atomic structure, and temperatures that would vaporize any known material instantly. The gravitational prison of Sagittarius A* is surrounded by a torture chamber of extreme physics. The study of matter crossing this cosmic point of no return has revealed some of the most exotic physics accessible to human observation. When gas clouds or stellar material approach the event horizon, they heat up to temperatures of billions of degrees. creating plasma conditions more extreme than those found in stellar cores. This superheated material glows brilliantly in X-rays and gamma rays, creating some of the most luminous objects in the universe. Recent observations have detected hot spots of material orbiting just outside the event horizon of Sagittarius A* at velocities approaching 30% the speed of light. These glowing knots of plasma complete full orbits around the black hole in just minutes, providing direct observational evidence of matter at the very edge of the gravitational prison. The orbital velocities are so extreme that relativistic effects become clearly apparent. Dr. Fariol Joel, who studies black hole environments, explained the significance of these observations. We rewatching matter in its final moments before disappearing forever from our observable universe. It is like seeing the last light from a cosmic lighthouse before the signal is cut off permanently. The magnetic field structure near the event horizon creates additional complexity in this gravitational prison. As charged particles spiral around the black hole, they generate magnetic fields that become twisted and amplified by the black hole's rotation. These magnetic fields can become so intense that they dominate over gravity itself in certain regions, creating jets of material that escape the black hole's influence at nearly the speed of light. This magnetic escape mechanism represents one of the few ways that energy can be extracted from a black hole system. The process, called the Blandford-Zanayak mechanism after the physicists who described it, allows rotating black holes to power some of the most energetic phenomena in the universe. While Sagittarius A* appears to be relatively quiet in this regard, other supermassive black holes use this mechanism to launch jets extending millions of light years into space. The rotation of Sagittarius A* itself adds another dimension to its gravitational prison. Like all massive objects, the black hole spins, and this rotation drags spacetime around with it in an effect called frame dragging. Near a spinning black hole, the very geometry of space and time becomes twisted, creating regions where standing still relative to distant stars becomes impossible. The boundary where this frame-dragging effect becomes unavoidable is called the ergosphere, and it extends slightly beyond the event horizon. Within the ergosphere, all matter and energy must rotate with the black hole, whether they want to or not. This region represents a kind of intermediate prison, not as absolute as the event horizon, but still a region where normal concepts of space and time break down. Current measurements suggest that Sagittarius A* rotates relatively slowly compared to the maximum possible rate for a black hole. If it were spinning at maximum rate, the ergosphere would extend much farther from the event horizon, and the effects of frame dragging would be even more dramatic. The black hole's rotation rate affects everything from the stability of nearby orbits to the efficiency of energy extraction mechanisms. Perhaps the most profound aspect of this gravitational prison is how it challenges our understanding of the nature of information and reality. Once something crosses the event horizon, it becomes causally disconnected from the rest of the universe. No signal, no information, no influence of any kind can travel from inside the event horizon to the outside world. In effect, the contents of a black hole exist in a separate pocket universe, forever isolated from everything else. This isolation raises deep questions about the nature of physical reality. If information disappears into black holes and can never return, does it still exist in any meaningful sense? Does the interior of a black hole represent a genuine destruction of information? Or does it continue to exist in some form inaccessible to external observation? These questions connect black hole physics to some of the deepest problems in quantum mechanics and thermodynamics. The gravitational prison of Sagittarius * isn't just a cosmic curiosity, it's a natural laboratory where the most fundamental questions about reality are being tested under conditions impossible to recreate anywhere else. As our observational technology becomes increasingly sophisticated, we're beginning to peer ever closer to this ultimate boundary. What we discover there may revolutionize our understanding of space, time, and the fundamental nature of existence itself. Chapter 6. Stellar Dance in the Cosmic Ballroom Surrounding Sagittarius A*. Stars perform a dance of such breathtaking violence and beauty that it challenges every assumption about celestial mechanics. These aren't the stately, predictable orbits of planets around stars. These are death-defying pirouettes around an invisible partner that could annihilate them in an instant. The stellar dance near our galactic center reveals gravity in its most extreme and artistic form. The most famous performer in this cosmic ballet is a star designated S2, a blue giant containing about 15 times the mass of our Sun. S2 follows an elliptical orbit so extreme that it approaches within 120 astronomical units of Sagittarius A*, closer than Pluto orbits our Sun, while reaching speeds of nearly 5,000 kilometers per second at closest approach. To put this in perspective, if Earth were moving this fast, we could travel from New York to Los Angeles in just 4 seconds. Watching S2 complete its 16-year orbit around the black hole is like watching a cosmic bullet circle an invisible target. At its farthest point, called aphelion, S2 is about 1,000 astronomical units from the black hole, moving at a relatively leisurely 500 kilometers per second. But as it falls toward its closest approach, called perihelion, the star accelerates dramatically under the black hole's gravitational influence. Dr. Andrea Ghez, whose team has been tracking S2's orbit for over 2 decades, described the challenge of these observations. We needed to measure stellar positions with precision equivalent to detecting the width of a human hair at the distance of the Moon. And we had to do this through Earth's turbulent atmosphere while tracking objects moving at thousands of kilometers per second. The breakthrough came with adaptive optics technology that uses computer-controlled mirrors to correct for atmospheric turbulence in real time. These systems allow ground-based telescopes to achieve resolution sharp enough to track individual stars in the crowded galactic center environment. For the first time in human history, astronomers could watch gravitational physics play out in real time around a supermassive black hole. But S2 is just the headline act in a much larger stellar ensemble. Astronomers have now cataloged over 100 stars orbiting within a few thousand astronomical units of Sagittarius A*. These stars, collectively known as the S-stars, follow a remarkable variety of orbital patterns. Some have nearly circular orbits, while others trace elongated ellipses that bring them terrifyingly close to the point of no return. The star S62 holds the current record for the closest observed approach to Sagittarius A*, coming within just 120 astronomical units of the event horizon, so close that it experiences time dilation effects measurable from Earth. During its closest approach, S62 reaches velocities exceeding 7,500 kilometers per second, or about 2.5% the speed of light. At these speeds, Einstein's special relativity effects become clearly apparent. These extreme orbital velocities have allowed astronomers to conduct the most precise tests of Einstein's general relativity ever performed. As predicted by Einstein's equations, the orbits of stars like S2 show clear signatures of relativistic effects. The orbit precesses or rotates slightly with each passage around the black hole. This precession occurs because spacetime near the black hole is curved in ways that Newtonian gravity cannot explain. The observed orbital precession matches Einstein's predictions with stunning accuracy, providing compelling evidence that general relativity correctly describes gravity even under the most extreme conditions accessible to human observation. These measurements have ruled out many alternative theories of gravity and confirmed that Einstein's century-old equations remain valid in gravitational fields millions of times stronger than anything found in our solar system. But the stellar dance around Sagittarius A* reveals more than just confirmations of known physics. It also provides insights into the formation and evolution of this extreme stellar environment. The S stars are remarkably young. Most are massive blue giants that formed within the past few million years. This presents a puzzle, because the tidal forces near the black hole should prevent normal star formation processes. The leading theory suggests that these stars formed farther away and were subsequently transported into their current tight orbits through gravitational interactions. Some may have formed as part of binary star systems, with one member ejected when the pair encountered the black hole's gravity. Others may have been captured from stellar clusters that wandered too close to the galactic center. Dr. Reinhard Genzel, co-winner of the Nobel Prize for Galactic Center Research, explained the implications. The stars we observe today are telling us a story about the dynamical history of our galaxy as center. Each orbit is a fossil record of gravitational interactions that occurred over millions of years. The most dramatic events in this stellar dance occur when stars venture too close to the black hole as tidal radius, the distance at which the black hole's gravity begins to overcome the star's own gravity. When this happens, the star begins to stretch and deform, with material stripped away from its surface. These tidal disruption events create spectacular fireworks displays as stellar material heats up while spiraling into the black hole. In 2020, astronomers detected such a tidal disruption event involving a star designated S62. As the star made its closest approach to Sagittarius A*, telescopes detected a bright flare in infrared and X-ray emission, indicating that stellar material was being stripped away and heated to millions of degrees. The event lasted several hours, providing real-time observations of a star being partially consumed by a black hole. These tidal interactions don't always result in complete stellar destruction. Many stars survive multiple close encounters with the black hole, though they may lose some of their outer layers in the process. Some stars appear to have been inflated by tidal heating, becoming larger and more luminous than normal stars of their mass. This inflation process may explain why some of the S stars appear unusually bright and extended. The stellar population near Sagittarius A* also includes more exotic objects than ordinary stars. Astronomers have detected what appear to be stellar remnants, white dwarf stars, and neutron stars in tight orbits around the black hole. These dense objects represent the final evolutionary stages of massive stars, and their presence near the black hole provides clues about the long-term dynamical evolution of the galactic center environment. Perhaps the most intriguing members of this stellar dance are objects that may not be stars at all. Some orbital tracks suggest the presence of massive, dark objects that could be intermediate mass black holes with masses between stellar mass and supermassive scales. If confirmed, these objects would provide crucial insights into how supermassive black holes form and grow over cosmic time. The choreography of this stellar dance is constantly changing. Computer simulations show that the gravitational interactions among stars, combined with their interactions with the central black hole, create a chaotic dynamical system. Over millions of years, stellar orbits can change dramatically. Some stars will be ejected from the system entirely, while others will spiral inward toward eventual destruction. This ongoing dynamical evolution means that the stellar environment we observe today represents just a snapshot of a continuously changing system. The current generation of S stars will eventually be replaced by new stars, either formed in situ or captured from elsewhere in the galaxy. The dance continues indefinitely, with new performers taking the stage as old ones exit through ejection or consumption. Recent observations have pushed the boundaries of this stellar census even closer to the black hole. The next generation of extremely large telescopes, currently under construction, will be able to detect stars in even tighter orbits around Sagittarius A*. These observations will provide increasingly precise tests of general relativity and may reveal entirely new aspects of black hole physics. The ultimate goal is to observe stars so close to the black hole that they orbit within just a few gravitational radii of the event horizon. At these distances, the orbital periods would be measured in minutes rather than years, and the relativistic effects would be so extreme that they would provide tests of physics impossible to conduct anywhere else in the universe. As we push our observational capabilities to their limits, the stellar dance around Sagittarius A* continues to reveal new secrets about the most extreme gravitational environment in our cosmic neighborhood. Each orbital measurement brings us closer to understanding not just how black holes work, but how they shape the evolution of galaxies and the cosmos itself. Chapter 7. Impossible Observations for Decades. The task of observing Sagittarius A* directly seemed utterly impossible. How do you photograph something that absorbs all light? How do you observe an object whose defining characteristic is its complete invisibility? The challenge was like trying to photograph the inside of a cave while standing outside in daylight, except the cave was 26,000 light years away and surrounded by a fog of cosmic dust that blocked 99.9% of all visible light. The breakthrough came from a revolutionary realization. While black holes themselves emit no light, they dramatically affect everything around them. The matter spiraling into a black hole heats up to billions of degrees, creating a glowing accretion disk that acts like a cosmic lighthouse. The black hole's enormous gravity bends light around it, creating a shadow against the bright background of this superheated material. If telescopes could achieve sufficient resolution, they might be able to photograph this shadow directly. But the technical challenges were staggering. The angular size of Sagittarius A*'s event horizon, as seen from Earth, is approximately 50 microsecons, equivalent to spotting a grapefruit on the surface of the Moon. No single telescope on Earth, no matter how large, could achieve this resolution. The laws of physics governing diffraction simply wouldn't allow it. Observing the galactic center black hole would require a telescope effectively the size of our entire planet. The solution emerged from a technique called Very Long Baseline Interferometry, or VLBI. Instead of building one impossibly large telescope, astronomers could combine signals from multiple telescopes spread across vast distances, effectively creating a virtual telescope as large as the separation between the instruments. The technique had been used successfully for decades in radio astronomy, but applying it to the galactic center would push the technology to its absolute limits. Dr. Shep Dolman, who led the Event Horizon Telescope project, described the magnitude of the challenge. We were essentially trying to create a virtual telescope the size of Earth itself, synchronized to picosecond precision, to photograph something that shouldn't be photographable. The engineering challenges alone seemed almost insurmountable. The Event Horizon Telescope, or EHT, represents perhaps the most ambitious observational project in the history of astronomy. The network combines signals from radio telescopes scattered across 6 continents, from Hawaii to Spain, from Chile to the South Pole. Each telescope must be equipped with atomic clocks precise to billionths of a second, because even tiny timing errors would destroy the delicate interference patterns needed to create high-resolution images. The choice of radio wavelengths was crucial to the project's success. While optical light from the galactic center is almost completely absorbed by interstellar dust, radio waves at millimeter wavelengths can pierce through this cosmic fog with minimal absorption. At a wavelength of 1.3 millimeters, the EHT could peer directly into the heart of our galaxy with unprecedented clarity. But even radio waves face obstacles near the galactic center. The region around Sagittarius A* contains clouds of hot, ionized gas that scatter radio waves. Blurring the image like atmospheric turbulence affects optical telescopes. This interstellar scattering creates a fundamental limit to the sharpness of images, regardless of how large the virtual telescope becomes. To overcome this limitation, the EHT team had to develop sophisticated computer algorithms that could distinguish between real features of the black hole and artifacts created by interstellar scattering. These algorithms use the physics of light scattering to deblur the observations, recovering details that would otherwise be lost to the turbulent interstellar medium. The data requirements for EHT observations are staggering. Each telescope in the network generates data at rates of several gigabits per second during observing sessions. This data must be recorded on specialized hard drives and physically transported to central processing facilities, because no internet connection can handle the massive data volumes involved. A single night of EHT observations generates more data than is transmitted across the entire global internet in the same time period. Processing this data requires some of the most powerful supercomputers on Earth. The raw telescope data must be correlated with picosecond precision, accounting for Earth's rotation, atmospheric effects, and the relative motion of all telescope sites. The process is so computationally intensive that it can take months to process a single night's worth of observations. The first major success of the EHT came not from imaging Sagittarius A, but from observing an even more distant and massive black hole in the galaxy M87. In 2019, the project released the first direct image of a black hole shadow, showing the distinctive ring of glowing material surrounding the dark central region where no light can escape. This image provided visual confirmation of theoretical predictions made decades earlier. But imaging Sagittarius A proved even more challenging than M87. While M87's black hole is thousands of times more massive than Sagittarius A, it's also much more distant. From the perspective of angular resolution, both black holes appear roughly the same size in the sky. However, M87's black hole accretes material at a steady rate, creating a relatively stable image over timescales of hours to days. Sagittarius A*, by contrast, is highly variable. The material around our galactic center black hole changes on timescales of minutes, creating a constantly shifting pattern of bright spots and dark regions. Attempting to image Sagittarius A* is like trying to photograph a constantly changing kaleidoscope with an exposure time of several hours. Dr. Sira Markov, a key theorist for the EHT project, explained the challenge. M87 is like photographing a mountain. It sits still while you take the picture. Sagittarius A* is like photographing a puppy that won't stop moving. We had to develop entirely new techniques to handle the rapid variability. The solution involved sophisticated algorithms that could track and model the changing brightness patterns around Sagittarius A* throughout the observation period. These algorithms essentially create movies rather than still images, showing how the glowing material moves and changes as it orbits just outside the black hole's event horizon. The variability itself provides crucial scientific information. The timescales of brightness changes reveal the orbital periods of material near the event horizon, allowing astronomers to measure the black hole's mass and spin with unprecedented precision. The patterns of variability also test theoretical models of how magnetic fields and turbulence affect the behavior of hot gas in strong gravitational fields. Beyond direct imaging, the EHT observations provide tests of Einstein's general relativity under the most extreme conditions, accessible to human observation. The shape and size of the black hole's shadow depend on the precise nature of spacetime curvature near the event horizon. Any deviations from Einstein's predictions would show up as distortions in the observed shadow. The polarization of radio waves from the galactic center provides another layer of information about the extreme physics near Sagittarius A*. As light passes through the twisted magnetic fields around the black hole, Its polarization direction rotates in ways that reveal the structure and strength of these fields. These measurements provide insights into how magnetic fields affect the accretion process and potentially power jets of material ejected from the black hole. Recent EHT observations have begun to reveal the three-dimensional structure of the magnetic field around Sagittarius A *. These fields appear to be dynamically important, potentially controlling how efficiently the black hole can accrete material and launch outflows. Understanding these magnetic field structures is crucial for comprehending how supermassive black holes affect their host galaxies. The success of the EHT has opened new frontiers in black hole astronomy. Future observations will achieve even higher resolution by adding more telescopes to the network, including space-based observatories that could extend the virtual telescope's size beyond Earth's diameter. These enhanced observations will probe even closer to the event horizon, potentially revealing new physics in the most extreme gravitational environments. The technological innovations developed for the EHT have applications far beyond black hole astronomy. The precision timing techniques, data correlation algorithms, and image reconstruction methods are finding uses in fields ranging from global positioning systems to medical imaging. The project represents a remarkable example of how pushing the boundaries of fundamental science drives technological innovation. Perhaps most importantly, the EHT observations are providing humanity's first direct visual evidence of objects whose existence was purely theoretical just decades ago. The images of black holes transform these cosmic monsters from mathematical abstractions into observable realities, bringing the most extreme predictions of modern physics into the realm of experimental verification. As the technology continues to improve and new telescopes join the global network, the impossible observations of today will become routine measurements of tomorrow. The black hole at the center of our galaxy, once hidden behind an impenetrable veil of dust and distance, is finally beginning to reveal its secrets to human observation. Chapter 8. Event Horizon. The event horizon of Sagittarius A* represents the most profound boundary in physics, a mathematical surface beyond which the very concept of beyond loses all meaning. This invisible barrier, stretching roughly 12 million kilometers from the black hole center, marks the point where space-time curvature becomes so extreme that escape becomes not just difficult, but fundamentally impossible according to the laws of physics. Understanding the event horizon requires abandoning human intuition about boundaries and surfaces. Unlike the edge of a cliff or the surface of a planet, the event horizon isn't made of matter or energy. It's purely geometric, defined by the point where the escape velocity equals the speed of light. Since nothing can travel faster than light, anything crossing this boundary enters a region of spacetime from which no causal influence can ever return to the outside universe. The name event horizon itself captures the profound nature of this boundary. In physics, an event is something that can potentially affect other events through causal connections. The horizon represents the limit of observable events. Beyond it lies a realm where events can influence nothing in our observable universe. It's literally the edge of knowable reality from the perspective of external observers. For Sagittarius A*, this horizon encompasses a sphere roughly the size of Mercury's orbit around our Sun. Within this volume lies mass equivalent to 4.3 million suns, compressed to a density that becomes infinite at the center. The horizon itself contains no mass. It's simply the geometric boundary where space-time curvature reaches a critical threshold. What makes the event horizon particularly strange is how it appears different to different observers. From the perspective of someone falling toward the black hole, the horizon represents no special barrier at all. A hypothetical astronaut could cross the event horizon without experiencing anything dramatic at that moment. The gravitational forces would feel smooth and continuous, with no sudden jolt or obvious sign that the point of no return had been passed. But from the perspective of external observers, that same astronaut would appear to slow down and freeze at the event horizon. Unfreezing, their image becoming increasingly redshifted and dim until it faded below the detection threshold. To outside observers, nothing ever quite reaches the event horizon. It just appears to approach it asymptotically over infinite time. This difference in perspectives highlights one of the most counterintuitive aspects of black hole physics. The event horizon exists in a different temporal reference frame than the rest of the universe. Time dilation effects become so extreme near the horizon that the concept of simultaneity between inside and outside becomes meaningless. Recent observations with the Event Horizon Telescope have provided humanity's first direct glimpse of this cosmic boundary. While the EHT cannot resolve the event horizon itself, it can image the shadow that the horizon creates against the backdrop of glowing material in the accretion disk. This shadow appears as a dark circular region surrounded by a bright ring of superheated plasma. The size and shape of this shadow provide precise measurements of the black hole's mass and spin. Einstein's equations predict exactly how large the shadow should appear for a black hole of given mass, and the EHT observations confirm these predictions with remarkable accuracy. The measured shadow diameter corresponds to approximately 2.6 times the event horizon radius, exactly as predicted by general relativity. The edge of this shadow, called the photon sphere, marks another critical boundary around the black hole. At this distance, light rays can orbit the black hole in unstable circular paths. Photons that venture inside the photon sphere spiral inexorably toward the event horizon, while those that remain outside can potentially escape to distant observers. This creates the sharp edge visible in EHT images. The region between the photon sphere and the event horizon represents a kind of gray zone where light can exist but cannot escape. Photons in this region follow increasingly tight spirals around the black hole before finally crossing the event horizon and disappearing forever. This spiraling light creates complex gravitational lensing effects that contribute to the detailed structure visible in EHT observations. Dr. Dimitrios Saltis, a leading theorist in black hole imaging, explained the significance of these observations. For the first time, we're seeing the photon sphere and event horizon shadow predicted by Einstein's equations. We're literally looking at the edge of spacetime itself. The material near the event horizon experiences some of the most extreme physical conditions in the universe. Gas spiraling toward the black hole heats up to temperatures exceeding 1 billion degrees, hot enough to strip electrons from atomic nuclei and create a plasma more extreme than anything found in stellar cores. At these temperatures, matter radiates primarily in X-rays and gamma rays, creating some of the most energetic emission processes known. The orbital velocities of material near the event horizon approach significant fractions of light speed. Recent observations have detected hotspots in the accretion disk orbiting at velocities exceeding 30% the speed of light, completing full orbits around the black hole in just minutes. At these speeds, relativistic effects become clearly apparent, with Doppler shifting and time dilation creating complex patterns in the observed emission. The magnetic fields near the event horizon reach strengths that would be impossible to achieve in any laboratory. As electrically charged particles spiral around the black hole, they generate magnetic fields millions of times stronger than Earth's magnetic field. These fields become so intense that they can dominate the dynamics of the accretion flow, potentially controlling how efficiently material can approach the event horizon. The interaction between magnetic fields and the black hole's rotation may provide a mechanism for extracting energy from the black hole itself. According to the Blandford's Nyack mechanism, magnetic field lines threading through the ergosphere can tap into the black hole's rotational energy, launching jets of material at nearly light speed. While Sagittarius A* appears relatively quiet in this regard, other supermassive black holes use this mechanism to power some of the most energetic phenomena in the universe. The event horizon also plays a crucial role in one of the deepest puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Every physical process must preserve the total amount of information in the universe. But black holes appear to violate this principle by permanently removing information from our observable universe. Stephen Hawking's discovery that black holes should slowly evaporate through quantum effects only deepened this paradox. If black holes evaporate completely, what happens to the information that fell past their event horizons? This question has driven decades of research into quantum gravity and the fundamental nature of spacetime. Recent theoretical developments suggest that the event horizon may not be as absolute a barrier as once thought. Some theories propose that quantum effects near the horizon create subtle correlations between material falling into the black hole and radiation escaping from it. These correlations might preserve information in a highly scrambled form, resolving the paradox while maintaining the essential features of black hole physics. The study of event horizons has also revealed deep connections between gravity, thermodynamics, and information theory. Jacob Bekenstein and Stephen Hawking showed that black holes possess entropy proportional to their surface area rather than their volume, suggesting that the information content of a region of space is fundamentally limited by its boundary rather than its interior. This holographic principle has profound implications for our understanding of spacetime itself. It suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. The event horizon may represent the ultimate expression of this principle. As our observational capabilities continue to improve, we're approaching the ability to study material in its final moments before crossing the event horizon. Next-generation telescopes will achieve sufficient resolution to track individual hotspots in the accretion disk as they spiral toward the point of no return. These observations will provide unprecedented tests of general relativity and may reveal new physics operating at the boundary between the quantum and gravitational regimes. The event horizon remains one of the most profound concepts in modern physics, a boundary that separates the knowable from the unknowable, the observable from the forever hidden. Its study has revolutionized our understanding of gravity, space-time, and the fundamental nature of reality. As we peer ever closer to this cosmic boundary, we continue to discover that the universe is far stranger and more wonderful than our earthbound intuitions could ever suggest. Chapter 9. Feeding time. Every few years, something extraordinary happens near the event horizon of Sagittarius A*. The usually quiet monster at the center of our galaxy suddenly awakens from its cosmic slumber and begins to feed. During these dramatic episodes, known as flaring events, the black hole's luminosity can increase by factors of hundreds within minutes, creating fireworks displays visible across multiple wavelengths of the electromagnetic spectrum. These feeding events offer astronomers a rare glimpse into the most extreme physical processes in the universe. When material finally succumbs to the black hole's gravitational pull and spirals past the point of no return, it doesn't disappear quietly. Instead, it heats up to temperatures exceeding 1 billion degrees, radiating more energy in minutes than our sun produces in years, creating cosmic lighthouses that can be detected from thousands of light years away. The trigger for these feeding events can vary dramatically. Sometimes a gas cloud wandering through the galactic center ventures too close to Sagittarius A* and gets shredded by tidal forces. Other times, stellar winds from nearby massive stars provide a steady stream of material that occasionally clumps together into denser concentrations. Most dramatically, entire stars can be partially or completely disrupted by the black hole's gravity, providing sudden banquets of stellar material. Dr. Sarah Markov, who studies black hole accretion processes, described the violence of these events. When Sagittarius A* feeds, we're witnessing the most efficient conversion of mass to energy allowed by physics. Material crossing the event horizon releases gravitational potential energy equivalent to nuclear fusion, but concentrated into a region smaller than our solar system. The accretion process itself is a complex ballet of plasma physics, magnetic fields, and relativistic mechanics. As material spirals toward the black hole, it forms what's called an accretion disk, a swirling vortex of superheated gas and dust. But near Sagittarius A*, this disk is neither stable nor well-behaved. Instead, it's a chaotic, turbulent structure where magnetic fields twist into complex geometries and hot spots race around at significant fractions of light speed. The temperatures achieved during feeding events are almost incomprehensible. At billions of degrees, atomic nuclei are stripped of all their electrons, creating a plasma so hot that it radiates primarily in X-rays and gamma rays. For comparison, the core of our Sun reaches about 15 million degrees. The feeding zones around Sagittarius A* are more than 100 times hotter than the nuclear furnace that powers our nearest star. These extreme temperatures create radiation so intense it would be lethal to any form of life at astronomical distances. During major flaring events, Sagittarius A* briefly becomes one of the most luminous X-ray sources in our galaxy. If our Sun were suddenly replaced by the galactic center during a feeding event, the radiation would sterilize Earth's surface within seconds. The magnetic fields generated during these events reach strengths that dwarf anything found elsewhere in the galaxy. As electrically charged particles spiral around the black hole at near-light speeds, they create magnetic fields millions of times stronger than Earth's magnetic field. These fields become so intense that they can actually dominate the gravitational forces in certain regions, creating complex feedback effects that influence how efficiently the black hole can continue feeding. Recent observations have revealed that the feeding process occurs episodically rather than continuously. For most of the time, Sagittarius A* is relatively quiet, accreting material at a rate equivalent to consuming about 1 Earth mass per year. But during flaring events, this rate can increase by factors of thousands, as the black hole suddenly gorges itself on whatever material happens to be available. The variability timescales of these flaring events provide crucial information about the size and structure of the emission region. Observations show that the brightness of Sagittarius A* can change significantly on timescales as short as minutes. This rapid variability implies that the emitting region must be extremely compact, no larger than the distance light can travel in the observed timescale. For flares lasting minutes, the emission must originate from a region no larger than a few times the event horizon radius. This places the emission source in the most extreme gravitational environment accessible to human observation, where space and time are warped to their maximum extent and the laws of physics operate at their absolute limits. The Event Horizon Telescope has begun to resolve the spatial structure of these feeding events, revealing hot spots that orbit the black hole at velocities approaching 30% the speed of light. These observations provide direct visual evidence of matter in its final moments before crossing the event horizon, completing orbital periods that last just minutes rather than years. Dr. Zoll, a leading expert in black hole observations, explained the significance. We're literally watching material disappear from our observable universe in real time. It's like seeing the cosmic equivalent of water going down a drain, except the water is heated to billions of degrees and moving at relativistic speeds. The physics of these feeding events extends far beyond simple gravitational attraction. The process involves a complex interplay of general relativity, magnetohydrodynamics, and plasma physics. As material approaches the event horizon, it experiences frame-dragging effects from the black hole's rotation, causing the space-time itself to twist and rotate. This creates preferential directions for material to approach the black hole and may help explain the observed orbital structure of the accretion flow. The magnetic field structure near the event horizon plays a crucial role in determining how efficiently material can be accreted. Strong magnetic fields can create pressure that actually prevents material from falling directly into the black hole, forcing it to spiral around in complex patterns before finally succumbing to gravity. This magnetic pressure can also launch jets of material away from the black hole, allowing some of the infalling material to escape rather than being consumed. Current observations suggest that Sagittarius A* may be launching such jets, though they appear much weaker than those seen from more actively feeding supermassive black holes in other galaxies. These jets represent one of the few ways that black holes can influence their surroundings beyond their immediate vicinity, potentially affecting star formation and galaxy evolution across vast distances. The feeding behavior of Sagittarius A* also provides insights into the long-term evolution of our galaxy. Computer simulations suggest that supermassive black holes and their host galaxies evolve together through a delicate balance of feeding and feedback. When black holes feed too aggressively, they can heat up surrounding gas and temporarily shut off their own food supply. This creates episodic cycles of feeding and quiescence that may explain the current relatively quiet state of our galactic center. The material being consumed during these feeding events represents a tiny fraction of what's available in the galactic center environment. Despite its enormous gravitational influence, Sagittarius A* is actually a rather inefficient eater. Most of the gas and dust in the galactic center never gets close enough to be accreted, instead being swept away by stellar winds or heated to temperatures where it can escape the black hole's gravitational pull. This inefficiency may be crucial for the habitability of our galaxy. If Sagittarius A* were feeding more aggressively, it could create radiation levels and outflows that would disrupt star formation throughout the galactic center and potentially affect the entire galaxy's evolution. The current feeding rate appears to be in a sweet spot where the black hole can grow slowly while allowing the galaxy to continue forming stars at a healthy rate. Future observations with next-generation telescopes will provide even more detailed views of these feeding events. Plans are underway to expand the Event Horizon Telescope network with additional radio telescopes and potentially space-based interferometry. These enhanced capabilities will allow astronomers to create movies of the feeding process, tracking how hotspots evolve and disappear as material crosses the event horizon. The study of black hole feeding has also revealed deep connections to fundamental physics. The efficiency of converting rest mass to energy during accretion approaches the theoretical maximum allowed by Einstein's mass-energy equation. This makes accreting black holes among the most efficient energy conversion mechanisms in the universe, more efficient than nuclear fusion and exceeded only by matter-antimatter annihilation. As we continue to study these cosmic feeding frenzies, we're gaining insights not just into black hole physics, but into the fundamental nature of matter, energy, and space-time under the most extreme conditions accessible to human observation. Each flaring event provides a natural laboratory where the predictions of theoretical physics can be tested against the ultimate reality of nature's most extreme environments. Chapter 10. Galactic Heartbeat. Deep within the heart of our galaxy, Sagittarius pulses with a rhythm that influences everything around it across vast scales of space and time. This cosmic heartbeat doesn't follow the steady cadence of a biological heart, but instead beats in irregular bursts of energy and matter that ripple outward through the galactic center, shaping the formation of stars, the distribution of gas, and the evolution of our entire cosmic neighborhood. The metaphor of a heartbeat captures something profound about the role of supermassive black holes in galactic evolution. Just as a heart pumps blood through circulatory systems, supermassive black holes pump energy and material through their host galaxies, creating feedback loops that regulate growth and development on cosmic scales. This feedback process may be one of the most important mechanisms governing how galaxies form and evolve over billions of years. The galactic heartbeat operates through several different mechanisms, each contributing to the black hole's influence on its surroundings. During active feeding periods, Sagittarius A* launches jets of high-energy particles that can extend thousands of light years from the galactic center. These jets carry energy and momentum far beyond the black hole's immediate gravitational sphere of influence, potentially affecting star formation rates throughout the galaxy's central regions. Dr. Elliot Quatert, who studies black hole feedback processes, explained the far-reaching nature of these effects. When we talk about a supermassive black hole's influence on its galaxy, we're not just talking about the immediate neighborhood around the black hole. We're talking about processes that can affect star formation and gas dynamics throughout the entire galactic bulge. The energy output during these feedback events is staggering. When Sagittarius A* undergoes major feeding episodes, it can release energy equivalent to millions of supernovae over timescales of thousands to millions of years. This energy heats surrounding gas clouds to temperatures where they can no longer collapse to form new stars, effectively regulating the galaxy's star formation rate. This regulatory mechanism may explain why massive galaxies tend to have surprisingly low star formation rates compared to what their gas content would suggest. The central black holes in these galaxies have grown large enough that their feedback effects can shut down star formation across vast regions, creating what astronomers call red and dead galaxy systems with little ongoing star formation, despite containing enormous amounts of gas and dust. The galactic heartbeat also operates through more subtle gravitational effects. As stars and gas clouds orbit through the galactic center, they experience the black hole's gravity in ways that alter their trajectories and energies. Some objects gain energy and are ejected from the central regions entirely, while others lose energy and spiral inward toward eventual destruction. This gravitational processing continuously reshapes the stellar population near the galactic center. Computer simulations reveal that this gravitational influence extends much further than initially expected. The black hole's gravity affects the orbits of stars throughout the galactic bulge, creating resonances and dynamical structures that influence how stars move and interact. These effects accumulate over cosmic timescales, gradually altering the overall structure and evolution of the galaxy. The timing of the galactic heartbeat varies dramatically over different time scales. On short time scales of minutes to hours, we observe rapid flaring events as material crosses the event horizon. On intermediate timescales of years to decades, we see longer-term variations in the black hole's activity level. On cosmic timescales of millions to billions of years, the black hole undergoes major growth phases that can dramatically alter its host galaxy's properties. Recent observations have revealed that Sagittarius A* appears to be in a relatively quiet phase of its evolutionary cycle. Compared to supermassive black holes in other galaxies, our galactic center is feeding at a remarkably low rate, consuming material equivalent to only about 1 Earth mass per year. This quiescent state may be temporary, representing just one phase in a longer cycle of activity and dormancy. Evidence for past periods of much higher activity comes from observations of the galactic center's large-scale structure. Astronomers have detected giant radio lobes and X-ray bubbles extending thousands of light years above and below the galactic plane. These structures, known as the Fermi bubbles, appear to be the remnants of enormous outflows that occurred when Sagittarius A* was much more active in the relatively recent past. Dr. Meng Su, who helped discover the Fermi bubbles, Describe their significance. These structures tell us that our galactic center was much more active just a few million years ago. The black hole went through a feeding frenzy that ejected enough energy to create structures larger than many entire galaxies. The formation of the Fermi bubbles required Sagittarius A* to consume material at rates thousands of times higher than current levels, possibly triggered by a major merger with another galaxy, or the disruption of a massive star cluster near the galactic center. The energy released during this event was sufficient to blow hot gas and energetic particles far out of the galactic plane, creating the observed bubble structures. These bubble structures demonstrate how the galactic heartbeat can operate on truly cosmic scales. The material ejected during the bubble formation event has traveled thousands of light years from the galactic center, carrying energy and momentum to regions that are only weakly bound by the galaxy's gravity. Some of this material may escape the galaxy entirely, contributing to the enrichment of intergalactic space with heavy elements forged in stellar cores. The galactic heartbeat also influences the chemical evolution of our galaxy. During active periods, the black hole's outflows can transport heavy elements synthesized in the galactic center to more distant regions. This chemical mixing process helps explain why stars throughout the galaxy show relatively uniform abundances of elements heavier than hydrogen and helium, despite the fact that these elements are primarily produced in the galactic center and inner disk. The regulation of star formation by black hole feedback has profound implications for the development of planetary systems and potentially life itself. If supermassive black holes didn't provide this regulatory mechanism, galaxies might exhaust their gas supplies too quickly, creating stellar populations dominated by very massive, short-lived stars that would prevent the formation of stable planetary systems. Conversely, if black hole feedback were too strong, it might prevent star formation entirely, creating dead galaxies with no ongoing stellar birth. The current level of activity from Sagittarius A* appears to be in a Goldilocks zone that allows continued star formation at a moderate rate while preventing runaway stellar production that could disrupt galactic structure. The study of galactic heartbeats has also revealed connections between supermassive black holes and the large-scale structure of the universe. Cosmological simulations show that galaxies and their central black holes evolve together through complex feedback loops that operate over billions of years. The properties of galaxies we observe today, their sizes, stellar populations, and gas content all bear the imprint of their central black hole's evolutionary histories. This coevolution process may explain some of the remarkable correlations observed between black hole masses and galaxy properties. The mass of a galaxy's central black hole is tightly correlated with the mass of its stellar bulge, the velocity dispersion of its stars, and other galactic properties. These correlations suggest that black holes and galaxies regulate each other's growth through feedback processes operating over cosmic time. Future observations will provide increasingly detailed measurements of our galaxy's heartbeat. Next-generation X-ray telescopes will be able to trace the energy and momentum output from Sagittarius A* with unprecedented precision. Radio observations will map the magnetic field structure of outflows and jets. Optical and infrared surveys will trace how black hole activity affects star formation rates in different regions of the galaxy. The concept of a galactic heartbeat has transformed our understanding of how galaxies work. Rather than being passive collections of stars and gas, galaxies are dynamic systems where central black holes play active regulatory roles. The supermassive black hole at the center of our galaxy isn't just a massive object sitting in the galactic center. It's the beating heart that helps keep our cosmic home alive and evolving. This heartbeat will continue for billions of years into the future, slowly but inexorably shaping the evolution of the Milky Way. Understanding its rhythm and effects provides crucial insights into our galaxy's past and future, revealing how the seemingly destructive force of a supermassive black hole can actually be essential for creating and maintaining the cosmic environment that makes life possible. Chapter 11. Future Fate. The story of Sagittarius A** is far from over. This cosmic monster that has shaped our galaxy for billions of years will continue to evolve, grow, and influence its surroundings for trillions of years to come. But its future is intimately connected to the fate of our entire galaxy. The approaching collision with Andromeda and the ultimate destiny of all supermassive black holes in an expanding universe. Over the next billion years, Sagittarius A* will continue its slow but steady growth through the accretion of gas, dust, and occasional stellar material. At its current feeding rate of roughly 1 Earth mass per year, the black hole will approximately double its mass over the next 10 billion years. This growth will gradually increase its gravitational influence, potentially altering the orbital dynamics of stars throughout the galactic center and affecting the structure of the galaxy itself. But the black hole's growth rate won't remain constant. As Sagittarius A* becomes more massive, its gravitational reach will extend farther into the galaxy, potentially capturing more material and entering phases of more rapid growth. Computer simulations suggest that supermassive black holes can undergo episodic growth spurts triggered by galaxy mergers, gas infall events, or changes in the large-scale structure of their host galaxies. The most dramatic event in Sagittarius A**'s future will occur in approximately 4.5 billion years when the Milky Way collides with the Andromeda galaxy. This cosmic collision will fundamentally alter both galaxies, creating a new elliptical galaxy that astronomers have dubbed Milky Way. During this merger process, Sagittarius A** will eventually merge with Andromeda's central supermassive black hole, creating an even more massive monster at the heart of the combined system. Dr. Abraham Loeb, who has studied galaxy mergers extensively, described the anticipated collision. When two galaxies merge, their central black holes eventually spiral together and merge in one of the most energetic events possible in the universe. The merger of Sagittarius A** with Andromeda's black hole will release energy equivalent to converting several solar masses directly into gravitational waves. The merger process itself will be spectacular beyond imagination. As the two black holes spiral together over millions of years, they will create ripples in spacetime called gravitational waves. These waves will carry away orbital energy, causing the black holes to spiral inward faster and faster until they finally merge in a cataclysmic event lasting just milliseconds. The gravitational waves produced by this merger will be detectable by future gravitational wave observatories from distances of billions of light years. The merger will briefly outshine all the stars in the observable universe in gravitational wave energy, creating ripples in spacetime that will propagate across the cosmos at the speed of light. But even this cosmic collision represents just one chapter in Sagittarius A**''s extended future. The merged black hole will continue to grow and evolve in the new galaxy created by the Milky Way Andromeda collision. It will accrete material from stellar winds, capture passing stars, and potentially merge with other smaller black holes as the new galaxy settles into a stable configuration. As the universe continues to expand and cool, the environment around supermassive black holes will gradually change. Star formation rates will decline as galaxies exhaust their gas supplies and fewer new stars are born to replace those that die. The stellar population around Sagittarius A** will gradually age, with massive stars dying off and leaving behind white dwarfs, neutron stars, and stellar mass black holes. This aging stellar population will provide new types of food for the supermassive black hole. White dwarf stars that wander too close to Sagittarius A* will be tidally disrupted, providing sudden bursts of accreting material. Binary star systems will gradually spiral together due to gravitational wave radiation. occasionally producing spectacular explosions or merger events that can feed material to the central black hole. On even longer time scales, the expansion of the universe itself will begin to affect Sagittarius A**'s environment. As space expands, galaxy clusters will gradually separate, and individual galaxies will become increasingly isolated. The Milky Way galaxy will eventually find itself alone in an expanding void, with the nearest neighboring galaxies receding beyond the observable horizon. This cosmic isolation will gradually starve supermassive black holes of new material, with fewer galaxy mergers to trigger gas inflows and no external sources of material. Black holes like Sagittarius A** will be forced to survive on whatever resources remain within their host galaxies. The accretion rate will gradually decline as the available material is consumed or ejected through stellar evolution processes. But even in this far future, Sagittarius A** won't remain unchanged forever. Stephen Hawking's theoretical work predicts that all black holes, no matter how massive, will eventually evaporate through a quantum mechanical process now known as Hawking radiation. This process occurs because quantum fluctuations near the event horizon can create pairs of particles, one of which falls into the black hole while the other escapes, carrying away energy. For supermassive black holes like Sagittarius A**, the Hawking evaporation process is incredibly slow. The time required for complete evaporation is proportional to the cube of the black hole's mass, making it virtually eternal by human standards. Sagittarius A* would take approximately 1,087 years to evaporate completely, a time span so vast that it makes the current age of the universe seem like an instant. Dr. Dome Page, who calculated black hole evaporation timescales, put this in perspective. The time it would take for Sagittarius A* to evaporate is longer than the time it would take for a monkey randomly typing to reproduce the complete works of Shakespeare, not once, but billions upon billions of times. During the final phases of evaporation, the black hole would gradually shrink and heat up, eventually releasing its remaining mass in a final burst of energy. This endpoint represents the ultimate fate of all black holes in the universe, assuming no new physics intervenes to alter the evaporation process. The far future evolution of Sagittarius A* is closely tied to fundamental questions about the ultimate fate of the universe itself. If the universe continues to expand and cool indefinitely, supermassive black holes may become the last remaining structures in a cold, empty cosmos. They would serve as the final repositories of matter and energy, slowly releasing their contents back into space through Hawking radiation. Some theoretical scenarios suggest more exotic possibilities for the far future. If the universe undergoes a big rip due to accelerating expansion, even black holes might be torn apart by the expansion of space itself. Alternatively, if vacuum decay occurs, the fundamental properties of space and time might change, altering the physics that governs black hole behavior. Recent discoveries in cosmology and particle physics have opened up additional possibilities for black hole evolution. Dark energy, which drives the accelerating expansion of the universe, might interact with black holes in unexpected ways. Some theories suggest that black holes could serve as windows into extra dimensions or connections to other universes, potentially altering their long-term evolution. The study of black hole futures has also revealed deep connections to information theory and the fundamental nature of physical laws. If black holes truly destroy information when they evaporate, it would represent a violation of quantum mechanics that might require new physics to resolve. Understanding how this information paradox is resolved could provide insights into the ultimate theory of quantum gravity. Future observations will continue to refine our understanding of how supermassive black holes evolve. Next-generation gravitational wave detectors will observe black hole mergers throughout the universe, providing direct measurements of how these objects grow and change over cosmic time. Improved models of galaxy evolution will show how black hole growth is connected to the formation of large-scale structure in the universe. The legacy of Sagittarius A* extends far beyond its own eventual fate. The black hole has played a crucial role in shaping our galaxy and making it suitable for the formation of planetary systems like our own. Understanding its past, present, and future provides insights into the cosmic processes that have made life possible and will continue to influence the universe's evolution. As we peer into the far future of our galactic center, we see a story that encompasses the grandest scales of space and time. From its formation in the early universe to its eventual evaporation in the cosmic far future, Sagittarius A* represents both the ultimate expression of gravitational physics and a window into the deepest mysteries of cosmic evolution. Chapter 12. Ultimate Truth. After our journey through the darkest depths of our galaxy, we arrive at a profound realization that challenges everything we thought we knew about cosmic architecture. The supermassive black hole at the center of the Milky Way isn't just an object in our galaxy. It is the reason our galaxy exists at all. This invisible monster that seemed so terrifying and destructive when we began our exploration is actually the fundamental organizing principle that makes our cosmic home possible. The ultimate truth about Sagittarius A* is that it represents a perfect example of cosmic symbiosis. The black hole and the galaxy exist in a delicate balance where each shapes and enables the other. Without the gravitational anchor provided by the central black hole, the Milky Way's spiral structure couldn't maintain its elegant form. Without the galaxy to feed it material and provide a gravitational context, the black hole couldn't have grown to its current size or sustained its influence over cosmic time. This symbiotic relationship extends to scales both vast and intimate. On the largest scales, Sagittarius A* helps regulate the formation of stars throughout our galaxy, ensuring that star formation proceeds at a rate that allows for the development of stable planetary systems. On smaller scales, the heavy elements forged in the violent environment near the black hole are dispersed throughout the galaxy, providing the raw materials necessary for rocky planets and the complex chemistry that makes life possible. Dr. Martin Rees, one of the leading theorists in black hole physics, captured this profound connection. The supermassive black holes and galaxy centers aren't cosmic accidents, they're integral parts of the cosmic ecosystem. Understanding them is essential for understanding how the universe creates structures capable of supporting complexity and life. The discovery and study of Sagittarius A* has revolutionized our understanding of cosmic evolution. Before astronomers knew about supermassive black holes, galaxies seemed like random collections of stars held together by gravity. Now we understand that galaxies are highly organized systems with central black holes serving as gravitational engines that drive their long-term evolution. This understanding has profound implications for our place in the cosmos. Every atom in your body was forged in stellar cores and dispersed through space by processes ultimately governed by the gravitational influence of Sagittarius A*. The sun's orbit through the galaxy, the formation of our solar system, and the chemical elements that make life possible all bear the imprint of our galaxy's central black hole. The journey to understand Sagittarius A* has also pushed the boundaries of human technology and scientific understanding. From the development of radio astronomy to the construction of the Event Horizon Telescope, our quest to comprehend the galactic center has driven innovations that benefit all of science. The techniques developed to study black holes are now used in fields ranging from medical imaging to global communications. Perhaps most importantly, studying Sagittarius A* has provided unprecedented tests of our most fundamental theories about the nature of reality. Einstein's general relativity, proposed over a century ago based on purely theoretical considerations, has been confirmed with extraordinary precision in the extreme gravitational environment near the galactic center. The orbital motions of stars, the gravitational time dilation effects, and the shadow of the black hole itself all match Einstein's predictions with remarkable accuracy. Yet our understanding remains incomplete. The center of our galaxy continues to harbor mysteries that challenge the boundaries of known physics. The information paradox remains unresolved. We still don't know what happens to information that falls into black holes, or how quantum mechanics and general relativity can be reconciled in the extreme environment near the event horizon. The magnetic field structure around Sagittarius A reveals complexities that we're only beginning to understand. These fields appear to play crucial roles in controlling how material approaches the black hole and how energy is extracted from the system, but the detailed physics of these processes remains an active area of research. Future observations will continue to reveal new aspects of our galactic center. The next generation of telescopes will achieve resolution sufficient to track individual hotspots as they orbit just outside the event horizon, providing real-time observations of matter in its final moments before disappearing from our observable universe. These observations may reveal new physics operating at the boundary between quantum mechanics and gravity. The upcoming extremely large telescopes will be able to detect even more stars in tight orbits around Sagittarius A *, potentially finding objects that complete full orbits in just a few years or even months. These observations will provide increasingly precise tests of general relativity and may reveal deviations from Einstein's theory that could point toward new physics. Space-based gravitational wave detectors will eventually be sensitive enough to detect the subtle gravitational waves produced by objects orbiting near supermassive black holes. These observations will provide a completely new way of studying the galactic center, using ripples in spacetime itself rather than electromagnetic radiation. The study of Sagittarius A* has also revealed deep connections between black hole physics and the fundamental constants of nature. The masses of supermassive black holes appear to be tightly correlated with properties of their host galaxies, suggesting that the formation of these objects is governed by universal principles that we're only beginning to understand. This correlation raises profound questions about the nature of cosmic fine-tuning. If the laws of physics were slightly different, or if the fundamental constants had different values, would supermassive black holes still form? Would galaxies still develop the organized structures we observe? Would the universe still be capable of creating the complex environments where life can emerge? The ultimate truth about Sagittarius A* may be that it represents one expression of deeper principles governing how complexity emerges from simplicity in our universe. The same gravitational physics that creates these cosmic monsters also enables the formation of stars, planets, and ultimately life itself. The black hole at the center of our galaxy isn't separate from the story of life. It's an integral part of that story. As we've seen throughout our journey, Sagittarius A* exists at the intersection of the largest and smallest scales in physics. It's massive enough to influence the structure of our entire galaxy, yet compact enough that quantum effects near its event horizon may govern its ultimate fate. Understanding it requires bringing together insights from cosmology, particle physics, thermodynamics, and information theory. The monster at the center of our galaxy has taught us that the universe is far more interconnected than we once imagined. Events occurring near the galactic center, 26,000 light-years away, have shaped the environment that allowed our solar system to form and life to emerge. We are not separate from the cosmic drama playing out around supermassive black holes. We are products of it. Perhaps the most humbling realization from studying Sagittarius A* is how much we still don't know. Despite decades of observations and theoretical work, fundamental questions remain unanswered. What happens inside the event horizon? How did the first supermassive black holes form in the early universe? What role will they play in the universe's ultimate fate? These unanswered questions ensure that Sagittarius A asterisk will continue to be a focus of scientific investigation for generations to come. Each new observation, each technological advancement, each theoretical breakthrough brings us closer to understanding not just what lies at the center of our galaxy, but what it means for our understanding of reality itself. The journey to comprehend the galactic center has transformed from a question about our cosmic neighborhood into an exploration of the deepest principles governing existence. In studying the most extreme object in our local universe, we've gained insights into the nature of space, time, matter, energy, and information that extend far beyond astronomy. As you look up at the night sky and see that hazy band of the Milky Way stretching overhead, remember that you're seeing the edge-on view of a vast cosmic structure organized and maintained by an invisible monster 26,000 light-years away. That monster isn't your enemy. It's the gravitational architect that made your existence possible. The ultimate truth about what lies at the center of the Milky Way is that it's not just the heart of our galaxy. It's one of the fundamental organizing principles that makes our universe capable of creating wonder, beauty, and life itself. Throughout this journey into the heart of our galaxy, we've discovered revelations that challenge every human intuition about reality. We've learned that the center of the Milky Way contains an invisible monster with the mass of 4.3 million suns, compressed into a region smaller than our solar system. We've watched stars dance around this cosmic predator at velocities that mock our earthbound understanding of motion. And we've realized that this seemingly destructive force is actually the gravitational architect that makes our galaxy and our existence possible. But perhaps the most profound insight isn't about Sagittarius A* itself, but about what its discovery means for our understanding of our place in the cosmos. For thousands of years, humans looked up at the stars and wondered whether we were alone, whether our existence had cosmic significance, whether the universe was designed for life or hostile to it. The supermassive black hole at our galactic center provides a surprising answer to these ancient questions. As you go about your daily life after learning about Sagittarius A*, you carry with you a new understanding of your cosmic heritage. Every breath you take contains atoms forged in stellar furnaces whose formation was guided by the gravitational influence of our galaxy's central black hole. The sun that warms your face follows an orbit through the galaxy that has been shaped by this invisible monster for billions of years. The very stability of our solar system depends on the organized structure of our galaxy, which exists only because of the gravitational architecture provided by Sagittarius A*. When you face challenges in your life, remember the incredible forces that had to align perfectly across cosmic history to make your existence possible. The formation of our galaxy, the synthesis of heavy elements in stellar cores, the dispersal of those elements through galactic winds driven by black hole activity, the formation of our solar system in just the right location to avoid the violent environment near the galactic center, all of these processes had to work together with exquisite precision. Consider the scale of what we've discovered. The black hole at the center of our galaxy is so massive that it bends space and time themselves. Yet it represents only a tiny fraction of the galaxy's total mass. Our entire solar system, everything we've ever known or experienced, would fit comfortably within the orbital path of just one of the S-stars dancing around Sagittarius A*. Yet from this cosmic perspective, your thoughts, dreams, and experiences are no less meaningful. They're part of the same cosmic story that includes stellar death spirals and the birth of galaxies. The journey to understand Sagittarius A* has required humanity to develop new eyes for seeing the cosmos. We've learned to observe with radio telescopes that pierce through cosmic dust, infrared detectors that reveal hidden stellar populations, and gravitational wave detectors that sense ripples in spacetime itself. Most remarkably, we've created a telescope the size of our planet to photograph the shadow of an object that absorbs all light. These achievements represent the best of human curiosity and ingenuity working together to answer fundamental questions about reality. Yet, for all our technological sophistication, the most important discoveries often come from simply asking the right questions. What is at the center of the Milky Way? This question seems simple, but answering it required revolutionizing our understanding of gravity, space, time, and the fundamental structure of the universe. Sometimes the most profound truths are hidden behind the most basic curiosities. You are not separate from the cosmic drama we've explored tonight. You are made of stellar material, organized by galactic processes, and governed by the same physical laws that create black holes and bend spacetime. Your consciousness arose in a universe where matter can organize itself into structures complex enough to contemplate their own existence. The fact that atoms forged in stellar cores billions of years ago can arrange themselves into brains capable of understanding. Black holes represents one of the most remarkable achievements in cosmic evolution. The supermassive black hole at the center of our galaxy connects you to the largest structures and longest timescales in the universe. Its formation began when the universe was young and will continue far into the cosmic future, long after our sun has died and our planet has been reduced to dust. Yet, it also connects you to the smallest scales of reality, where quantum mechanics meets general relativity and the nature of information and reality becomes fundamentally uncertain. You exist at the intersection of these cosmic scales, a conscious observer capable of comprehending both the quantum fluctuations that may cause black holes to eventually evaporate and the galactic dynamics that shape the evolution of entire stellar systems. The invisible monster at the heart of our galaxy has taught us that the universe is far stranger and more wonderful than our ancestors could have imagined. Space and time are not fixed stages on which cosmic drama unfolds. They are dynamic participants in the story, warping and bending under the influence of matter and energy. Causality itself becomes negotiable near event horizons, where effects can precede causes and information can become forever isolated from the rest of reality. But perhaps the most beautiful revelation is how this strangeness enables rather than prevents the emergence of complexity in life. The same gravitational physics that creates objects so extreme they trap light forever also creates the conditions necessary for stellar birth, planetary formation, and chemical evolution. The universe's capacity for both ultimate destruction and exquisite creativity stems from the same fundamental laws operating across different scales and conditions. The story of Sagittarius A* is ultimately a story about the power of human curiosity and scientific investigation. Just a few centuries ago, the existence of black holes was pure speculation, mathematical solutions to equations that seemed too extreme to represent physical reality. Today, we can watch matter disappear into these cosmic monsters in real time, test the predictions of general relativity with extraordinary precision, and use black hole physics to probe the deepest questions about the nature of existence. This transformation from speculation to direct observation represents one of humanity's greatest intellectual achievements. It required generations of scientists building upon each other's work, pushing the boundaries of technology and theory to address questions that seemed unanswerable. The collaboration between observers and theorists, between different cultures and nations, between past insights and future possibilities, demonstrates what we can accomplish when we work together to understand our cosmic home. As we look toward the future, the supermassive black hole at the center of our galaxy will continue to serve as a natural laboratory for exploring the frontiers of physics. Each new observation brings us closer to understanding how quantum mechanics and gravity can be unified, how information is preserved in black hole interactions, and how the universe creates and maintains the complex structures that make life possible. The ultimate answer to what is at the center of the Milky Way turns out to be far richer than any single response could capture. At the center of our galaxy lies a gravitational monster that shapes stellar evolution, a cosmic engine that regulates galactic dynamics, a natural laboratory where the laws of physics operate at their most extreme, and a reminder that the universe is capable of creating structures so profound they challenge our deepest understanding of reality itself. You are connected to this cosmic center not as a distant observer, but as an integral part of the same physical and evolutionary processes that created it. Your ability to contemplate the existence of Sagittarius A*, to understand its physics, and to appreciate its role in cosmic evolution, represents the universe becoming conscious of itself. In studying the monster at the center of our galaxy, we are ultimately studying the cosmic processes that made our own existence possible. If you made it this far in our journey, subscribe and give this video a thumbs up. Check out my exploration of how galaxies form and evolve, the hidden architecture of the universe. I'm sure you'll find it equally mind-expanding. The next time you see the Milky Way stretching across a dark night sky, remember that you're not just looking at a collection of distant stars, but at the edge-on view of a cosmic structure organized and maintained by one of the most extreme objects in the known universe, a supermassive black hole that serves not as a cosmic destroyer, but as the invisible architect of everything we call home.